Today we discuss application of
হ্যালো স্যার
yes
স্যার বলছি যে ফ্রম দ্য টেস্ট ট্রেস স্ট্যাটিস্টিক আর ম্যাক্সিমাম লেভেল মানে ম্যাক্সিমামটাতে মানে ওদের কি সবসময় কি একই রেজাল্ট হবে, সিমিলার রেজাল্ট হবে?
একই রেজাল্টই হওয়ার কথা। ওটা
And
নিয়ে
if they are different,
পরে
sir,
discuss
how
করব।
are we supposed to interpret?
পরে আমাকে ফোনে জিজ্ঞেস করুন।
Okay sir, okay, thank you sir.
So let we concentrate on vector autoregression, today's topic. So keep your device in silent mode to hear me better. So vector autoregression, application of vector autoregression with initial statistics, and today also we use the same data set as used in our last class, National Account Statistics, NAS data. Now, in the last class, we have performed co-integration test by considering three series, probably GDP at market price, aggregate consumption expenditure, as well as gross private fixed cost, that is the private investment expenditure. So we have taken three variables: one, GDP at market price, that is national income; another one, aggregate consumption expenditure; and the third one, aggregate private investment expenditure. By taking three variables, we have carried out co-integration test to look into whether the variables are causally related or not. Okay? So in continuation with our previous class, we
স্যার আগের দিন দুটো ভেরিয়েবল নিয়েছিল।
consumption and income and consumption,
log
PFC
GDP
or GDP.
GDP at market price, and
PFC,
PFC, that is private final consumption expenditure.
private final consumption expenditure.
Okay,
Yes sir.
so we have taken two variables, one for GDP, another for aggregate consumption expenditure. And by taking these two variables, we have carried out co-integration test, as well as probably Granger's two-step methods of co-integration test in finding out whether the variables are causally related or not. Okay, so in continuation with our previous class, today we extend our analysis in vector autoregressive framework. So you have to keep in mind.
স্যার একজন এন্ট্রি নিতে চাইছে, একটু অ্যাকসেপ্ট করে দেবেন?
মুশকিল, এই ক্লাস চলাকালীন ডিস্টার্ব করলে মানে ভীষণ প্রবলেম হয়, টাইম মতো আসবে না, এইগুলো খুব সমস্যা, তোমরা একদম রেসপন্ড করবে না। So we extend today by considering vector structure. So to understand the application of VAR with data, you have to keep in mind what we have discussed in third semester class, the basic structure, theoretical structure of vector autoregressive. So, and as you know, we perform vector autoregressive model. Vector autoregressive suggests autoregressive in vector form. So vector form means we have taken more than one variable together. So it is a multivariate model in time series econometrics. So when we have more variables and we are not sure which one is dependent and which one to be treated as independent variable, in that case we can treat all variables equally. That is, all variables are treated as a dependent variable. And in many cases, you can face this kind of problem. For example, in the case of income consumption data, the theory suggests national income depends on aggregate consumption. Again, theory suggests consumption expenditure depends on national income. So you are not sure in specifying a model whether consumption expenditure is to be considered as a dependent variable or whether income is to be considered as a dependent variable. So this type of problem may arise in many cases, because in many cases theory does not clear with which variable is to be considered as a dependent variable and which variable is to be considered as an independent. So in that case, the better option or safe option is to consider all variables to be a dependent variable. So this is the basic structure of vector autoregressive form. So vector autoregressive form means you have autoregressive equations, and the number of autoregressive equations will be equal to the number of variables. For example, if you have two variables, consumption and income, you can formulate two autoregressive equations. So in your system, you have two equations, and how many variables to be considered or how many regressors to be taken into account, that depends on the appropriate lag length in your model. So if you have three variables, you have three number of equations in your system. So in this way, the number of equations in a vector form will be equal to the number of variables you have considered. So we have to keep in mind the basic structure, and initially we can specify VAR model in terms of what is called the structural form of the VAR. And the basic problem in structural VAR is relating to the problem of estimation, because structural VAR normally could not be identified properly. So if we take into account the identification problem, we have to convert the structural VAR into a reduced form VAR. So reduced form VAR can be estimated by applying OLS or by applying maximum likelihood. And after estimating the reduced form VAR, our ultimate objective is to find out the structural VAR, not in the reduced form VAR, because the economic interpretation of the reduced form VAR and structural form VAR are not similar, they are different. So we have specified initially the model in the form of a structural VAR, and we are really interested in estimating this model. But to avoid some technical problems, we convert this structural VAR into a reduced form, and we estimate the model in reduced form structure. After estimating the model in reduced form structure, we have to find out the estimated values in structural form. So this will be determined uniquely if your model is identified properly. So identification problem is one of the problem you have to face in the case of a vector autoregressive structure while you estimate the model. So after estimating the model, we have to make some inference on the basis of this. So we will discuss all these issues with official statistics, national account statistics, as we have used in our previous class. Now, before moving into the data and the application with Stata, let we recapitulate the basic structural steps of our model. Okay, I'm just going through quickly because you need to know the steps to understand the meaning of the result you have in Stata output window. So just in quick format, because all of you aware with these kind of models in your semester 3. So this is the basic form of the structural VAR we have. So we have defined here the variable x in vector form. So x includes more number of x, x1, x2, x3, etc. And we can convert it into reduced form. So we can estimate this model. After estimating this model, we have got the estimated value of pi 1, that is pi 1 hat. And from pi 1 hat, we ultimately have to find out the value of gamma hat, capital gamma hat. So And before estimation, another problem we have to take into account, that is whether this reduced form, and if you compare this reduced form of the VAR, it is similar to the form you have familiar with, autoregressive form for a single variable. So xt is equal to phi naught plus phi 1 xt minus 1 plus et. So in this model, we assume that we are considering only one lag of the variable. So this is a VAR of order 1, as we have considered lag length up to 1. So if you include lag length more than 1, and accordingly you have higher order vector autoregressions. So this is actually the AR formulation in vector form. So as in the case of autoregressive form for a single variable, our basic problem was to find out whether the series is stationary or non-stationary. Similarly, before estimating the model, we have to look into from the reduced form whether this reduced form of the VAR is stationary or non-stationary. So we have to find out the stationary restrictions, and on the basis of that, we can judge whether the VAR we have is stationary or non-stationary. So if we assume this VAR structure is stationary one, because if it is stationary, we can estimate this model directly. But if it is not stationary, we cannot estimate this model directly. So in that case, we have to make some adjustment before estimation. So on the basis of the assumption that stationarity condition or stationarity restriction satisfies, in that case, we can express this VAR in a reduced form into this form. And this is similar to the single variable case. If you try to remember the basic formulation for single variable, it looks like similar. Okay, and we can find out the restriction for stationarity just similar to the case of a single variable. So as we have more than one variable here, we have to take into account the matrix pi 1. So we can form pi 1 minus lambda I equal to 0. So this is the characteristic equations in our case. And by solving these characteristic equations, we can find out the characteristic roots. And the characteristic roots in vector sense are called the eigenvalues. And if the values of the eigenvalues are less than 1, then we can say that there is no unit root in your vector form. And in that case, we can safely estimate this model, and we can formulate this model into a moving average form. Because if you try to remember, autoregressive form of a single variable can be converted into moving average if the variable is stationary. So under stationarity restriction, any autoregressive form can be converted into moving average of order infinity. So on the similar way, we can convert vector autoregressive model into a vector moving average form in this way. So why we want to convert vector autoregressive form into vector moving average? Because if you look at the structure of vector moving average, here we have expressed the values of the variable x2 as a function of the disturbance term innovations in the reduced form. So here we can look at the data generating process of the system as the function of the innovations or the error terms. And by analyzing this form, we can find out basic information, what we have called it the impulse response functions. So you are familiar with impulse response function. So to find out impulse response function, we have to convert the vector autoregressive form into a vector moving average form. So vector moving average form can be obtained only under the stationarity restriction. So if stationarity condition is satisfied, in that case, we can convert vector autoregressive model into a vector moving average model, and we can ultimately look at the data generating process of the variable in terms of the impulse response function. The term suggests impulse response, impulse, that is, if you provide some shocks into the system on a variable. Suppose we have two variables, x1 and x2, consumption, expenditure, and income. So you have two equations in your system. So two equations means you have two innovations or two error terms. So if any kind of shock appears in a particular error, so suppose a particular shock appears in your consumption series. So as if you look at the basic structure of the model, you can find out the error presence in the consumption function also affects the behavior of the income function. So if you put any shock in the error appeared in the consumption expenditure function, so it will be affected the model through the passing out the impulse from consumption to income. So in this way, we can find out how the impulse of a particular variable can affect the behavior of the other variables. So to find out this kind of effect, we need to find out the structure of the impulse response function. So to find out impulse response function, we have to convert the autoregressive form into a moving average form. Okay, so these are the basic theoretical structure we need to keep in mind before applying this model with data. Now, when we apply this model with Stata, we are using here Stata software, Stata 14 or Stata 15, whatever may be, the basics are the same. So let we look at very quickly the basic commands we can use in a VAR model. The main commands we can use in estimating a reduced VAR is VAR, simply VAR, or varbasic. So there are two options or two commands you can use, either VAR or varbasic. What is the difference between them? If you use VAR, then we can estimate the model after incorporating some constraint regarding the coefficients used in your model. But if we use the command varbasic, we cannot introduce any restriction. We can use or we can estimate the model simply without any restrictions by applying maximum likelihood or by applying OLS. And in that case, we can find out the behavior of the impulse response function. So it is a very simple model, varbasic. So this is the basic form of the vector autoregressive. That's why the command is called varbasic. So if we use varbasics, so we cannot complicate this model. We can get the result in a basic format. But if we want to change something, if we want to incorporate some constraints, if we want to incorporate some restrictions into our model, in that case, we should prefer to use this command VAR. Now, before estimating the model, you have to specify the appropriate structure of a VAR. And appropriate structure of a VAR depends on two things. One is the number of variables to be incorporated, and second one, the number of lags to be incorporated. So you have decided number of variables on the basis of your objectives. So if you want to estimate consumption income relationship, you have two variables. One variable is aggregate consumption expenditure, another variable is national income. So you have decided how many variables to be incorporated into the VAR. So this is one aspect. Another aspect is how many lags to be incorporated into the model. So you cannot specify arbitrarily how many lags. So that depends on the basics of the data generating functions of the variables you are using in your model. So in that case, you have to look into the basic behavior of the consumption expenditure series, basic behavior of the GDP series to find out the number of lags to be incorporated into the model. And you know, to find out the proper lag length, we have to use some criterion, information criterion, AIC criterion, SBIC criterion, etc. So in Stata, we can get the results or we can get the number of lags to be incorporated into the model by using the command VARSOC. So this command VARSOC provide you the appropriate lags you need to incorporate into this model. But if you have a Stata 14, Stata 15, etc. So if you are not performing this stage, in other words, logically, you need to find out the number of lags before estimating the model. But the present version of the Stata 14, Stata 15, if you just use the command var, so Stata by default will calculate the optimum lag length in the background. So in the background, this command will be effective if we use simple this command without using this. Okay, so we do not need to use VARSOC before estimating the model. But actually, if you want to understand the logic, so logically you have to first fix the number of lags to be incorporated. After that, you have to estimate the model. So you can estimate this model by using this command var, and this is basically the maximum likelihood estimation. And after estimation, we have to carry out some tests. They are called generally the diagnostic checks. So to check the diagnostics of your model, that is how good your model is fitted, for that purpose, we can perform some tests after estimation. One test is to find out whether the model is stable or not. So this is the stability condition. So what is the stability condition? Stability condition provides you whether your model is stationary or non-stationary. If your model is stationary, then the estimated result will provide you some meaningful interpretation. But if the model is not stable, that is the variables are non-stationary, in that case, the estimated model will not provide a meaningful interpretation. So to find out whether the VAR is stable or not, we can carry out this command VAR stable. So after executing this command, we can find out whether our VAR system is stable or not. Similarly, after estimating the model, we can use another command VAR grandeur. That is, why do we estimate a model? We have some purpose. So one purpose is to find out whether consumption expenditure causes national income, or to find out whether national income causes consumption expenditure. So to find out this kind of behavior, we have to carry out causality test. So one causality test is the grandeur causality test. Grandeur causality test can be carried out in two ways. One is by using a single equation system, another one by using a system of equations, that is after estimating a VAR. So after estimating a VAR, if we want to carry out grandeur causality, we have to execute the command VAR grandeur. So after that, we can carry out another test that is called the LM test for checking residual autocorrelation. So whether the residuals in your model are autocorrelated or serial correlation present or not, for that purpose we can carry out the LM test. And this LM test can be carried out by the command var LMAR. Okay. And all the behavior of your model based on the assumptions that the random variables are normally distributed. So we have to we have a few seconds left, and after that the session will stop. So after ending the session, we can start a next session for applications of the VAR models with data, what we are discussing in session 1. So after carrying out this test, you can carry out VAR normal to find out whether the residual, whether the error is normally distributed or not. And another thing we can do it, your model could be used for forecasting, and also we can find out the impulse response function. That is, if we push any shock or any shock involved in a series, so how this shock is transmitted to the another series. So this kind of exercise we can do with data. So in the next session, we directly move into the Stata software with data and how we can get the results and how we can interpret our results. Okay, so we stop now for the first session. So wait for 2 or 3 minutes to get a new link for the next session.